My name is Sebastian Bodenstein. I'm one of the framework developers for the Wolfram neural network framework. And my talk will be about the neural network framework in Wolfram language, where it's going, where it came from, and also larger industry trends in neural networks. So my name is Sebastian Bodenstein. I'm one of the two major developers on the neural network framework in the Wolfram language. And today's talk, there's been a lot of talks this whole week about applying neural networks to images, and there's been lots of talks this year. So I'm not going to go into massive details about learning how the framework works or things like this. I'm going to focus more on higher level pictures. So the first thing is, I want to discuss a bit, in the last year, what has happened in neural networks in the wider industry. And after that, I want to give some high-level ideas of sort of design principles that we have, that we follow for the neural network framework in the Wolfram language. And then also some upcoming features. So first of all, neural networks this last year have become even more popular than the year before that. And they've now become productionized in many places. So for example, for machine translation, in the past, Google has had a very customized and handwritten sort of pipeline for translating different languages. And they came to the conclusion that they couldn't improve it anymore. And they continuously, though, had issues with neural networks that they couldn't deploy it cheaply enough. That was the main problem. But last year, with some new hardware, they've finally gotten it that it's cheap enough to actually deploy feasibly. And so when this came online last year, for example, like the #1 trending Twitter topic on Google, on Japanese Twitter, above some cult anime series and some long-awaited new single from a girl idol supergroup, everyone wondered how had Google Translate become so uncannily artful. And the reason for that was because they'd switched to neural networks. Other kinds of things, so other highlights. So things like AlphaGo. So neural networks are one of the key pieces in the architecture for AlphaGo. They sort of evaluate how good they think a position is, and they can prune down the search space massively. So this was last year. And even like a few days ago, I think this was yesterday, this was announced, that DeepMind had gotten major improvements. Previously, it was pre-trained on human games, but now this new version is completely untrained on human games. It learns completely by itself. And its ELO rating is vastly higher than the one that beats Lee Sedol. OK, so other kinds of things. There's a lot of applications to robotics. So for example, this is from OpenAI. They have a nice little demo where a human can teach the robot to do something in VR, and the neural network has to learn how to imitate that. So it's a way of very quickly teaching robots what to do. And neural networks are very important for this as well, this architecture. OK, and other kinds of things. So for medical imaging, this was the front cover of Nature, lesions learnt. This was basically finding that you can have dermatologist-level classification of skin disorders with just a picture. And this is the case across medical imaging, that neural networks are becoming as good as doctors at diagnosing things. So there's just a whole slew of applications that have come out, from the important pieces of self-driving cars to speech recognition. Almost every system uses that. Natural language processing, from question answering to parsing. Sorry, this somehow weirdly came out here. This is, oh, oopsie. It looks a bit different if you don't go into the mode. So from sentiment analysis, and then also physics. Things like, there's a talk, I think, later on about using this for LIGO, for detecting gravitational waves. Again, you have massive amounts of data from detectors, and you need to make sense of it. And finance. There's also obviously like image processing. There's hundreds of applications. So what's happened is that the consequence of this widespread application is that companies have made specialized hardware. So the race to make hardware that all the different AI sort of application people want has heated up massively. So NVIDIA has a special chip called the Volta V100. This has specialized tensor cores that give a peak performance of 120 teraflops. And we're going to support this in 11.3, these upcoming V100. We're actually getting our own one soon to be able to test it out on. And then Google has, obviously, they've got tensor processing units, and Intel has a new chip that came out a few days ago. But no one, you can't get access to it yet. OK, so this is one major thing. So hardware, a lot of specialized hardware has come out. And the second thing is that there's been huge investment in frameworks. So NVIDIA, for example, has highly optimized neural network primitives called cuDNN. Intel came out to the game as well now with their own optimized primitives, which are still in the beta phase. We're going to support these as soon as they're ready, but they're still quite buggy. So this should speed up our CPU evaluation and training for neural networks, for convolutional neural networks, by about a factor of 10. So this will be a very nice speed up once we get that. And then framework-wise, it's become a huge undertaking to build these frameworks. So the major corporations like Microsoft, they have CNTK, Google has TensorFlow, Facebook has PyTorch and Caffe2, which they maintain, and they have a huge number of developers on that. And there's also MXNet, which we are using. And this is the only real major framework that is still alive. So certain frameworks like Theano also were not backed by a major corporation, but they've died now. So the only one surviving is MXNet. And it's actually, it's part of the Apache Foundation, and it's supported by lots of companies. So we also provide development support. And like Amazon is one of the major companies that supports it, NVIDIA, et cetera. So one more thing about MXNet is that one of the sort of major advantages that we have in our framework is that anything that, all the benefits that MXNet gets from its 400 contributors, and also the major corporations that sort of are building it, we automatically pass down to our users without any effort. So it's been a very nice collaboration with them. And also, we support now exporting to MXNet. So there's no lock-in anymore. So if you have a network, you can easily export to MXNet or import it from MXNet. And maybe just mention this very quickly, but MXNet is also building a compiler stack so that you can compile neural networks for any sort of device. This is maybe a bit small. Let me just make it bigger. So whether you want to compile it to ARM or x86 or JavaScript, this sort of support is coming at some point. And the last thing is that it's the official framework for Amazon Web Services. So Amazon has spent a huge amount of money improving MXNet to run efficiently on EC2. And we're in the process of making it easier for users and ourselves to train on EC2. So this is something that you can hopefully look forward to soon. OK, so the second sort of thing that I want to discuss is, one is industry's trends. But the second thing is, what sort of how is our framework going to evolve in the next year or two? And to understand how it's going and the sort of motivations for the things we're doing, you have to understand the sort of larger scale visions that we have for this framework and what we want it to be for. So lots of functionality in Mathematica is maybe a few users that want to use it, and the way you implement things, it depends. It's related to who's going to be consuming this functionality. So the first thing is that one of the major consumers of this functionality is now internal groups in Wolfram. So the machine learning group and the image processing group, we have a list of maybe like 50 different top-level functions that we want to use neural networks for that currently we cannot do. From things like speech recognition to question answering to image colorization to image description generation, image question answering. There's many, many of these functions. And we want to build this, or we're currently building this, with the framework. So a lot of the design that you might see and weird layers that pop up in the framework, they are because they're a requirement for our internal usage. So things like, simple things that are already there, things like image identify, Julio is busy working on image contents, which gives you like bounding boxes of all the objects in the image. And Timothy is going to work on speech recognition. So we're going to have a whole slew of applications that need this framework to be fast enough for very large-scale training. The second vision is that we want to make pre-trained networks a first-class citizen of the language. So it's actually very hard to train these networks. So you need huge amounts of data. So for some of these in the repository that we've got now, there's like maybe 100 million images that they've got that we use to train them. Also, the computation is not trivial. It requires sometimes multiple GPUs that train for sometimes a month, like for speech recognition. And most users just don't have that. So one of the sort of major pieces is the network repository that a few people have worked on. And basically, this repository is, probably Stephen showed this already at the keynote, but it gives you access to a growing number of networks, from things like image restylization, or maybe something like colorization, where you give it a black and white image, and the network can colorize it, for example. So, and we have very nice documentation for these networks. We can show them off, and you can easily download, for example, this notebook, either in the cloud or just download the notebook. So this is going to be a growing collection. And these are all accessible via netmodel. So in the language, you can just say netmodel, get me the model. Here's the net. And in this case, it wants to find key points of the face. So it finds where the eyes are, the nose, and the mouth. So, and yeah, these models, they range. Some of them are strange, like maybe they find not safe for work detection, if images are not safe for work, or finding like the geolocation of something, or finding how many objects there are in an image. In this case, it says, OK, there's 2 major objects in the image. So this collection is going to get, I don't know, maybe 100 networks or larger at some point. So the other thing is that they're also just very hard to define yourself, these networks. So huge amounts of effort have been expended to find the best architectures for neural networks, and you just cannot reinvent the wheel. So for images, things like ResNet are just very effective, and you almost always want to use that. And if you look at this architecture, each of these is a net graph inside here. And this is like a chain of like 100 of something of these. If you're going to write this out yourself, it's very messy and ugly. So it's very powerful to have these things available. And what we're sort of moving towards is this high-level paradigm that it's very difficult to write, like a good image recognition network right now. What you really want to do is you want to use pre-made components, and you just want to put them together. You want to cut things off them and then just stick them in where you want them. So if you have an image coming into the network, you want to say, OK, ResNet is good for image, put ResNet there. OK, we want to now generate some description. OK, we have a language model that we can plug on top of that. So there's like a much higher level paradigm that we want to introduce once we have a good collection of these networks. And also what's cool is that because they're all symbolic in Mathematica, these networks, you can do all kinds of operations, like take things or take parts, et cetera, et cetera. OK, so this is the second sort of vision that we're sort of moving towards. And one of the things that we need for this vision is also to train these things ourselves. OK, the last thing is that we want to make this framework as simple as possible, especially compared to other frameworks out there. So one basic thing is that we have a type system. So in this case, we string together some network, and it infers. It knows, OK, this is an embedding layer, and this requires a vector of, well, I've told what the input of the entire net chain is, but it infers exactly that this is a vector of size 2 of indices in the range of 1 to 4. And it does shape inference through the network, and type inference as well. And this is a feature that is really nice. And it allows things like very simple error messages. So for example, in this case, I've given integers 1 and 6. But of course, it's expecting integers between 1 and 4. And it tells you this. And if you use other frameworks like Keras and whatnot, there are very cryptic error messages that you get if you make even slight mistakes. The second sort of major principle that we've decided on that makes it quite different from other frameworks is this idea of encoders and decoders. So the idea is that you can attach a special pre-processing unit at the beginning. In this case, there's an image preprocessor. And the image preprocessor, it conforms the image. It puts it in the right color space. It removes the alpha channel. It might remove the mean image, all these sorts of things, these details that most frameworks have in separate scripts. We do this inside the network. And the same with the output. Often you want to output a class. You don't just want to have like a vector coming out of the thing. And this makes it very fun to use, because we can have a single network that we can export, and things like the classes live with the network. If you want to see what other sorts of frameworks look like, you can maybe I won't show this entirely. You can look at this yourself. But this is to make a single prediction, where you have to find the different scripts, the interpolation types for the resizing of the images, where the script's living, where's the mean image living. You have to transpose the image to get into BGR order. And then finally, you can do some classification. But of course, the classes are in a different scripts, so you have to do some processing. Yay, finally, we have that it's a tabby cat. So this is the official example from Caffe, for example. So this whole thing makes it very simple. And the last thing that are quite different from other frameworks is that we have first-class variable length sequence support. So it's actually very hard for neural network frameworks to deal with variable length sequences, because you always want to batch together examples. So on modern GPUs, it's vastly more efficient if you can have batches of examples that go together. But if you're doing things like matrix multiplication, you can't have ragged arrays. So other frameworks require all kinds of things, from padding the sequences to the same length, doing a bucketing procedure so that sequences that are similar get trained together, and then you can use single operation, like matrix multiplication operations on them. But for us, we've decided that we're going to put in a lot of work and make it much more complicated to implement, but we have native support for variable length. So for example, in this case, some strings this is of length 4. Okay, these are all of length 4. Okay, like this one, this is a different length from this one, length 5, and this one is length 4. So this is a very simple task. You have a string, and you just want to predict what the number is inside the string, given the string. So you get a sequence of characters, and you want to say, OK, given those sequence of characters, what did it add up to? So for us, it's very simple. You just have a simple net, and you can see inside here that these are variable length. So they can take in sequences of any size, and you can just train it. OK, this always gets messed up, unfortunately, for presentation mode. I'm not sure why. OK, I won't let it go all the way. It's maybe a bit of a waste of time. But OK, it's probably still bad enough it won't work. OK, somewhat reasonable. Not super good, but if you let it train a bit longer, it will work. So super simple. So other kinds of things, like you can make your own. It's extensible, this whole system. So we have support for defining your own recurrent operators. So people who want to do research in this, and they want to try out different architectures, all of this just automatically works out the box. And you can define with net fold operator, you can say, OK, here's a core little piece, and we want to fold this across a sequence. And we want to make this work on varying sequences efficiently, on GPUs, on anything. And it just works. And this is one of the things that we're moving towards as well, like these sort of high-level operators that take other layers and do sort of transformations on them. OK, so those are the three major principles. And stopping on this, I want to give a quick roadmap about where we're going. So in the first version, we basically had simple recurrent convolutional networks. We didn't have any RNNs. We did support GPU training, and we had a very limited set of layers. So in 11.2, our task has already been to add functionality. The major thing was to add recurrent network support with variable length sequence support, and also something like 30 new layers that we added in those 2 versions. And there's been massive numbers of small improvements, from like a multi-threaded image loader so that image training is fast enough if you're doing it out of core, to things like an MXNet import and exporter. OK, so the upcoming roadmap, again, remembering that one of the major things that we need is for internal training. And that sort of drives the things that we want. So one of the major features that people will, I think, enjoy a lot is net function. So first of all, a lot of nets don't fit into a static graph. So they have contingencies inside the computation graph. So it might depend on data. So here's a simple example. You have a convolution layer, and you do a computation. If the max of the input is greater than 2, then do something. Otherwise, do the convolution. So this sort of program, at the moment, you can't build that at all, because it's, yeah, like in a net graph, how would you build something like this? You can't put if statements in. But for NLP especially, for natural language processing, it's becoming more and more apparent that this is a good paradigm for lots of topologies. So things like PyTorch and Chainer, they basically only have this support. They only do dynamic graphs. So you write a program, and you can differentiate that program. And also things like, OK, so this is one big piece, that we can't do dynamic graphs at the moment. The second thing is that we can't do weight sharing very easily. So things like, you want to define a convolution layer and then use it twice or 3 times or whatever in the computation. That's a bit hard as well. And this allows this. And also, a lot of nets, it's very hard to write them as net graphs. It's much more natural to have variables and then use them in a program. So net function is going to solve all these together. It's going to have dynamic evaluation, so you can actually have if statements or while loops or do loops or anything else. And you can differentiate this entire program. And yes, it will become quite a general autograd engine that you can use for many other kinds of things that you want to differentiate, not just neural networks. And we also want to add things like custom layers. Once the compiler comes online, you can compile to LLVM, and then eventually you can compile LLVM to CUDA. This is something that internally we want a lot, because yeah, you often want to have custom layers. And for import-export, we want to have, there's a new format that is sort of common across many platforms. It's supported natively by 3 at the moment. But probably a lot of other frameworks were added as well, probably MXNet as well. And things like performance enhancements, like multi-GPU support. And for audio, we don't currently have good audio support. We don't have an audio encoder. We're getting that. The image group has helped us a lot to write this. So there's a whole bunch of things that we're getting. Maybe I'll just very quickly mention this last stuff as well. A key piece of frameworks is that training has to be easy. So internally, we're working on tools to make our own internal training easy by deploying training on EC2 with automatic reporting of losses and all that to a central server. And yeah, and this sort of infrastructure we want to make available to others as well. OK, cool. I think that's basically, I don't have to go through the conclusion.